Hello everyone, this is Orhan Erdem. In this video, I will be showing you how to evaluate the predictive performance of different models on Python. In this class, I will be using a dataset called 2023 Roxbury. This is the property assessments from Boston. This datasheet shows the property assessments of almost 6,000 houses. Every single row represents a house, and in the columns you see several characteristics of the houses. And column D shows the property assessment of that house in dollar terms. Basically, it is its value. And other columns represent different characteristics. Some columns, they are categorical columns, so I will exclude them in a moment. And then I will try to use all the characteristics of this data sheet to predict the value of the house. I get this data from this web page, data.boston.go. Basically, this is 2023 property assessment of houses in Roxbury district of Boston. And then I just cleaned up the data a little. Let's go ahead and open a Python file and start coding. Okay, first of all, here is how I create an empty Python file. And I will name this as 5 predictive performance. And then I will first import the necessary libraries. And then let me paste here where I found the data from, just for your information. And then now I will load the data. Okay, first of all, I will import the data. So I will give the name SSDF to my data frame that I will be using. The data is correctly imported from Excel file. Now let's take a look at the descriptive statistics. So this output shows the descriptive statistics of our data. If you take a look at the first row, which says count here, you can see that some variables such as gross area have missing values. So land square feet has 6,102 values, but gross area is 4,000 something. And some variables have even 3,000 something. So what I will do is I'm going to delete all of these missing data so that I will have a flawless estimation here. So as you can see, all the columns have 3,582 data. Now what I will do is to exclude the categorical variables from my data set and try to predict the outcome, which is total value. I imported my data and I defined what are the predictors and what is the outcome. The outcome is going to be the house appraisal value. The rest is going to be partitioned the data as train and test split. This is basically a very straightforward code. I'm just going to copy and paste it here and then run the code. So the code shows us the predictive performance of both the training side and the validation side of our data set. Okay, first part of these metrics belong to training data set. So these belong to training data set, and second part belongs to validation data set. All of these metrics you see here are evaluating predictive performance with a different measure. We have actual value of houses. So actual value of houses in Roxbury, which we will call Y, and then predicted values of house prices, which I will call Y bar. We don't see the predicted values right now, but we see how errors are performing. So this is the definition of error. Error is actual minus predicted. So actual house price minus predicted house price gives error. These are the average of errors in training part. These are the average of error in validation part. These are root mean square error in training part. This is the root mean square error in validation part, etc., etc. Basically, in this part of the class, what we did is we had numerical values of something, which is house prices, and we tried to predict those numerical values. And then, of course, we made some errors, and all of these metrics you see here are just showing us the performance of our errors. So the next question is, what if we predict classes instead of numerical values? For example, being an owner or non-owner is a class. Defaulting or non-defaulting is a class. In my next example, I will be using an Excel sheet which will be predicting a class membership instead of a numerical value. Now let's take a look at that example. Okay, this Excel sheet shows 3 columns. In column B, you see if a person actually defaulted or not. If it says 1 here, it means they defaulted. If it says 0, they did not default. Column A shows the predicted values of some models. So we don't know the models, but we know that these are the predicted probabilities. So the model predicts that the guy will default with 63% probability, with 28% probability, using some model. So the question is, how will I convert this probability to zeros or ones? So what I can do is I can use a cutoff value. I can say, for example, if the probability is higher than some number, say 0.5, then that means default. If it is less than 0.5, that means not default. So I can just write a column here. Let's call this predicted values. And then I will write a little comment here. If this value in column A is larger than 0.5, then this is going to be predicted as 1, otherwise 0. So these are my predicted values. For example, I use a cutoff value of 0.5. You can change cutoff value to 0.6. So as you can see, this correctly predicted. The second one is correctly predicted. Third one, fourth, sixth, seventh. Most of the values are correctly predicted until here. So this guy here, even though he did not default, my model predicts that he defaulted. The second one the same. So there are kind of some errors here. Let's talk about confusion matrix, which will introduce the idea of true positives, true negatives, false positives, and false negatives. Let's see. This table is called a confusion matrix. In field of machine learning, a confusion matrix is a specific table layout that allows visualization of the performance of an algorithm, typically a supervised learning one. Each row of the matrix represents the instances in an actual class, while each column represents the instance in a predicted class. So this is the actual case, positive or negative, and predicted condition, positive or negative. If something is actually positive and you correctly predict it as positive, this is called true positive. Similarly, if something is actually negative, you predict it as negative, then this is true negative. So these diagonals are the true conditions. The other diagonal is the false conditions. So let me give an example which will probably illustrate the situation better. Assume that there are 10 patients around, 6 of which are cancer, 4 of which are non-cancer. And this is our model. Assume that we positively predicted 4 out of 6 patients as positive cancer, but the 2 of them are predicted as negative, which is wrong. For the negative ones, there are 4 non-negative people here, so non-cancer ones. So one is incorrectly predicted as positive, but in fact it is not cancer. So these 3 guys are in fact not cancer, and then we correctly predicted them as negative. So there are a couple of definitions that we should make here. The first one is called overall error rate. So there are 2 errors here. So these red cells are errors. So I made one error here, I made another error here, so which are called false positive and false negative. So there is 1 false positive and there are 2 false negatives. So these are overall errors. So you add the overall errors, which is 2 plus 1, and then divided by total number of patients, which makes 30% of overall error. And there is accuracy here. The definition of accuracy is 1 minus the overall error rate, which is 70%. There are also other definitions. Sensitivity, which is defined as true positives divided by total positives, and specificity, which are true negatives divided by negatives. For example, sensitivity is defined as true positive divided by all positive. True positives are 4, overall positives are 4 plus 2. So 4 divided by 4 plus 2 is 6. And specificity defined as true negative divided by all negatives. So true negative is 3, all negatives are 4. So 3 divided by 3 plus 1 gives us specificity. These are all different definitions in a confusion matrix, but basically this is a confusion matrix and this is an example of confusion matrix. Coming back to our Excel sheet, there are people who defaulted and who did not default. And similarly, there are predictions which correctly predicted defaults and which incorrectly predicted defaults. Now let's import this data to Python and analyze the situation in Python. Okay, first let me import the default Excel sheet to Python. This is the overall outlook of our confusion matrix for the default data set. Basically, there will be people who either defaulted or non-defaulted, and then there will be predictions here, positive or negative. And so these red cells and the green cells will constitute my confusion matrix. And then now let's import this data to Python and make an analysis in Python. I will basically be interested in the first two columns, probability and the actual value. Even though there are no data here, because of the confusion matrix, the program is thinking that there is data here, but I'm going to be using only probability and actual value. So I will be going back and forth between Excel and Python. So let me show you something here. So let me mention the cutoff point once again. So for this cutoff point of 0.5, as you have seen before, we correctly predicted all of these values, but not those values. If you change the cutoff value from 0.5 to let's say 8, and then drag and drop, so this time these are all correctly predicted up to here. So this guy here is not correctly predicted. All of these true positives, true negatives, false positives, and false negatives, they change depending on the cutoff value. So if cutoff value changes, your performance changes. So what I will do in this code is to draw a graph which shows the performance of my confusion matrix based on the cutoff points. Okay, this chart shows us the performance of cutoff value and then shows the overall error and the accuracy. As you can see, the orange dashed line shows the overall error, and that overall error is the minimum when the cutoff value is somewhere around 0.5. And at that point, accuracy is the highest. Remember my confusion matrix and the example, cancer example? So we made a couple of definitions here: overall error rate, accuracy, specificity, sensitivity. In fact, there are like tens of definitions related to confusion matrix, all of which are listed in, for example, Wikipedia. So there are really an overwhelming amount of definitions related to this matrix. I will be showing you something called ROC curve, receiver operating characteristic curve, which is very related to the chart I showed you. So basically, this chart shows true positive rate versus false positive rate. True positive rate is sensitivity, and false positive rate is 1 minus specificity. So let's take a look at ROC curve so you would understand it better when we take a look at the Python code. Okay, this chart shows the ROC curve for my default data set. Basically, it shows true positive rate versus false positive rate with respect to cutoff values. As you might remember, there are tons of cutoff values. For every single cutoff value, there's a different true positive rate, and there's a different corresponding false positive rate. As you might remember, true positive rate is something that we aim for, we target for. That's why in this chart, better performance is reflected by curves that are closer to the top left corner, because that means true positivity rate is 1. So for every single cutoff value, if true positivity rate is 1, then that's a perfect model. The comparison curve is the diagonal, which reflects the average performance of a guessing classifier that has no information about the predictors or outcome variable. It's basically equally distributing the false positivity rate and true positivity rate in the diagonal. So for every false positivity rate, we have the same exact true positive rate. A common metric to summarize an ROC curve is the area under the curve, which is AUC, which ranges from 1 to 0.5. So 1 means perfect discrimination between classes, and 0.5 no better than random guessing. So in this example, ROC curve or area is 0.72, as you can see from the chart. Well, that's all about evaluating the predictive performance of models. If you want to learn more about these topics, please take a look at Chapter 5 of Data Mining for Business Analytics book. Hope to see you in the next videos.